In this chapter, we are going to discuss sequences. Now, as we think of a sequence, first let's just remember what is a function. Let's consider the function f of x equals x. Now what that does is for every input, which is an x value, we input into the function, and in this case, we get just that result back as an output value. So if I input the value 0.5, I would get the value 0.5 back as a result. I could continue input 1, I'd get 1 back as a result. We know how this function works. It would look like the straight line through the origin of slope 1. And the reason we represent it as this straight line is because we know the function takes on every input value, and there's infinitely many input values that we could input. So for instance, I showed 0.5 and 1, but we could also input 0.1, 0.15, 0.4999, 0.49999. And what that does is it traces out a continuous curve that shows the behavior of the function. Now, how is this related to sequences? Whenever we think of a sequence, it's a type of function, except the domain of the function is restricted. Now, earlier in this class, we looked at how to find the domain of a function. In this case, the domain is all real numbers. But what if we said, let's look at this function f of x equals x, where the domain is the positive integers. So in this case, I couldn't have a value here because that's not a positive integer, nor could I have a value here, here, here. In fact, the first starting point of the domain is 1. So let's redraw this graph with this new domain restriction. So some of the first elements of this domain would then be 1. The next element would be 2, 3, 4, 5, 6, and it would continue out that way. So for 1, we have height 1. If you plug 2 into the function, you get 2 back as a result. 3, you would get 3. And we can't link it by a line this time, because that would assume that we have all continuous values. So for instance, if I drew this line, that would be incorrect because that would assume the domain includes all real numbers between 0 and 6. But we're not including all real numbers between 0 and 6. We're only including the positive integers. So we have this point, this point, this point, this point, this point. This is the idea of a sequence. So it acts like a function except the domain is the positive integers. And the sequence notation, instead of using x, which generally could be all real numbers, we would instead say f of n equals n, because we think the domain is restricted to the natural numbers 1, 2, 3, 4, continuing on. So as we begin to talk about sequences, remember we would treat them just like we would treat regular functions. It's just that their domain is restricted to the positive integers. Now our definition is that a sequence is a function whose domain is a set of positive integers, and oftentimes we're going to be thinking about infinite sequence. An infinite sequence is a function whose domain is a set of positive integers, and it's going to have values out to infinity. A lot of times we'd like to express the terms of a sequence, and since the domain is the positive integers, we can actually talk about the first term, the second term, the third term, the fourth term. Whereas if we're talking about a function, we can't really talk about the first function value, because then you get to the question, what's the first value in the real numbers? There is no such first value. But if we're looking at only the positive integers, then we can't have a first value. The way we represent this is subscript notation. So generally, lowercase letters represent the terms of a sequence, A, B, C. And if you see A sub 1, that's the first term of the sequence. A sub 2, second term of the sequence. A sub 3, third term of the sequence, and so on. This would represent the nth term in the sequence, so some generalized nth term. And if we only let our sequence take on values from the first n positive integers, that would be called a finite sequence. So if we say it starts from here and it ends at this point. Now let's look at our first sequence. We have the sequence f of n, where the sequence relationship is whenever you take the input of a positive integer, the result is 1 over that positive integer squared. So in this case, we would write the first term as a sub 1. So we input 1 into the location of n, 1 over 1 squared, 1 over 1 is 1. We could find the second term of the sequence. We now say 1 over 2 squared, which would give us 1/4. The third term of the sequence, 1 over 3 squared, which would give us 1/9. Why don't you take a moment to find the fourth term and the fifth term? For the fourth term, we would find 1 over 4 squared, which is 1/16, and 1 over 5 squared would be the fifth term, 1/25. And often we write the terms of a sequence in order as a comma-separated list. So we could write the terms as the first term 1, comma 1/4, comma 1/9, comma 1/16, 1/25, and I think we see the pattern. It is the integer squared at the bottom. So it could continue out like this. And the way we represent that it continues forever is by writing enough terms of the sequence that the pattern is evident, and then comma ... Now sometimes we're given formulas to represent the sequence relationship. In this case, if you're given a formula where you can input an in value and get that exact term back, that would be called an explicit formula. And we'll compare this later to something called a recursive formula. And here we're asked to write the first 4 terms of the following sequences. The way our first sequence works, a sub n, is it takes the in value and it says we're going to say 2 times that in value minus 1, all divided by the in value. So for the first term, a sub 1, that would be 2 times 1 minus 1 divided by 1, which simplifies to 2 minus 1 over 1, which is 2. A sub 2 would be take the second, now n is 2, 2 times 2 minus 1 divided by 2. 4 minus 1 divided by 2 is 3/2. Now we continue a sub 3, 2 times 3 minus 1 divided by 3 is 6 minus 1 divided by 3. We get 5/3. Why don't we all take a moment to compute a sub 4? Two times 4 minus 1 divided by 4. That should give us 8 minus 1 divided by 4, or 7/4. Now our next sequence, b sub n, has a very characteristic piece, this -1 to the exponent n. What this term does is, let's think about it. -1 to the first power is -1. -1 to the second power is +1. -1 cubed is -1. -1 to the fourth is +1. What this term is going to do is it's going to oscillate the sequence back and forth between positive and negative numbers. So all this first term does is contribute positive or negative, and then the value of the sequence is really determined by this piece, n. So for our first term, b sub 1, we would take -1 to the first power times 1, because the n goes to the exponent and we're multiplying by that. That would give us -1 times 1, which is -1. b sub 2 is -1 squared times 2. We know -1 squared is a +1 times 2 would give us a +2. Now why don't we pause the video, and I think it'd be great for you to attempt the remaining ones, so find b sub 3, b sub 4, and then unpause the video to check your work. For b sub 3, we follow the formula. We take -1, raise it to the third power, and then multiply by 3. We know -1 cubed is -1 times 3 would give us -3. b sub 4, -1 to the fourth power, which would make it a +1 times 4, would give us a +4. And as expected, we see that our terms are going back and forth between negative, positive, negative, positive, all because of this -1 to the n. Next, we've got our sequence c sub n, and we see a similar formula here, except instead of being raised to the nth power, it's now to the n plus 1. So in this case, if it's raised to just the n, the first term is negative, right? Because -1 to the first power is a -1. But whenever we allow -1 to be raised to the n plus 1, that kind of shifts things down 1. Because now when you input 1, you're going to get -1 squared, which makes the first term positive. And it would make the second term negative, and the pattern would continue that way. All multiplied by 1 over n. So if we're writing out our first term, c sub 1, -1 raised to the exponent 1 plus 1 times 1 over 1. That's -1 squared times 1 over 1 is 1. That would be a 1 times 1, positive 1. Similarly, if we were finding the second term, -1 to the 2 plus 1, all times 1 over 2. Now we know this exponent becomes cubed, so we think, what is -1 cubed? Well, that's -1 times 1/2, and we get -1/2. Take a moment to pause the video and find c sub 3, c sub 4, and then unpause to check your work. We would take -1, raise it to the 3 plus 1 by the pattern, multiply it by 1 over 3. That's -1 to the 4th times 1/3, which is a positive 1 times 1/3. Now c to the 4th, -1 to the 4 plus 1 times 1 over 4. That's going to be equal to -1 to the 5th times 1/4, and we get -1/4. Now here we worked out the patterns by the formula step by step, but if we understand how the different pieces of the formula work, we can also determine the next terms even without using the formula in this case. What do we know is this term just keeps us going between positive and negative. So since I know the first term's positive, I automatically know the second term by this pattern should be negative, then the third term should be positive, the fourth term should be negative. So if I was to anticipate the fifth term in the sequence, since the previous one is negative, I should expect the fifth term to be positive. What's the other pattern? It's 1 over that number in our term. So I could estimate that C5 is positive 1/5. C6 is negative 1/6. C7 is positive 1/7. So you can think about how the pieces work and extrapolate out and find the later terms of the series that way as well. Now just for practice, let's look at B and take a moment to find B sub 37. Pause the video while you work. There we would take -1 to the 37th power and then multiply that by 37 based on how the pattern is set. Now we know -1 to any odd exponent is just -1. So the 37th term here is -37. Now one of the reasons I wanted us to calculate this b to the 37th is so that we could see if we're given an explicit formula, it's very easy to find later terms. And we're going to compare this soon to the idea of a recursive formula where it's not so easy to find the 37th or the 50th or the 75th term. So what makes something a recursive formula? A recursive formula is defined to be a formula that defines each term of the sequence using the preceding terms. So you can't just jump to some point in the sequence, you have to know all the terms that come before it to know the next term. And recursive formulas, because of how they work, will always state your initial term or terms of the sequence and then some kind of relationship between that and the next term. Our first example of a recursive formula is here. We are given at first the first term of the sequence, a sub 1 is 9. And then we're told if you want to find a later term, sum a sub n, what you would need to do is you would need to take 3 and multiply it by a sub n minus 1. Now let's pay attention to the subscripts here. If I tell you something is n and then something is n minus 1, we would realize that this is directly previous n, right? Because it's n minus 1. So in words, I should say one term is exactly equal to 3 times the previous term minus 20. So if you want to find the next term, you multiply the previous term by 3 and then subtract 20. And this formula holds for n values greater than or equal to 2. The reason it's greater than or equal to 2 is we've already got the first term, so this pattern only works past a certain point. And we're going to compare this to an explicit formula. So a recursive formula uses the sequence notation. This says you have to know the previous term. Whereas in our explicit formulas, it just said you had to know n, which is which term you wanted. It didn't have to know any of the actual terms in the sequence. It was just expressed in terms of a formula that we could substitute a value of n for, and we'd get that term. So let's find the first 5 terms of this sequence. Good news is we already know a sub 1 is 9. Now, how would we find a sub 2? If I was just directly following the formula here, n is 2. So it's 3 times a sub 2 minus 1 as a subscript minus 20, which simplifies to 3 times a sub 1 minus 20. A sub 1 in this case is 9. So that could be 3 times 9. Then minus 20, so that's 27 minus 20, I get the value 7. And you can work it out formula-wise like this if you prefer, but you could also kind of catch hold of the pattern and tell yourself, okay, it's 3 times the previous minus 20, the previous is 9, 3 times 9 is 27, minus 20, the answer is 7. Now notice we have to have a sub 2 to find a sub 3, because to find the next term, you have to know the previous. So to find a sub 3, I could either follow the formula, which I'll write out, 3 times the previous term, minus 20. What is the previous term? It's 7. So that's 21 minus 20, and I get 1 is the third term. Or I could say, okay, the third term is 3 times the previous, so 3 times 7 is 21, minus 20 gives me 1. Now how would I find the fourth term? I would say 3 times the previous term, so 3 times 1 is 3. Minus 7 gives me negative 4. Or you could go through the formula, 3 times the previous term, minus 20. What is the previous term? It's 1. So 3 times 1 is 3, minus 20 is negative 17, would be our answer. Sorry, when I was verbally describing it, I think I got the numbers mixed up, but you could think 3 times the previous term of 1 is 3, minus 20 would give us a negative 17. Finally, our fifth term, we could say 3 times the previous term minus 20. Our previous term is negative 17 minus 20. Now let's see, what is 3 times negative 17? That would give us negative 51 minus 20, and we get negative 71. So keep in mind the difference between the explicit formula and the recursive formulas. The explicit formula, you could just plug in any number you want for n, and that gives you that term. You don't have to know any other information about the previous terms. But a recursive formula, the formula depends on previous terms, so we've got to know what came before to find the next one. And this is where we see recursive formulas being a little more difficult to work with, because what if I asked you to find a sub 100? Think about in words, what would you have to do? Do we agree this formula says in order to know a sub 100, you'd have to take 3 times the 99th term minus 20. But what is the 99th term? We don't know that. How do you find the 99th term? You'd have to know the 98th term. And I think we see the pattern. I'd have to know all the terms from the 5th term up to the 99th term in order to get the 100th term. Whereas if we had an explicit formula, all you would have to do is plug n equals 100 into the formula, and you'd find that term. So recursive formulas are particularly difficult to work with if you want to find terms very far down the sequence, because to find that, you'd have to know everything that comes before. Now let's talk about how this formula works, and then I'm going to ask that you pause the video and attempt it on your own for practice. As I'm looking at this formula, I would say this is a recursive sequence right off the bat, because I see it's not listing n, it's listing a sub some n value, which is some term in the sequence related to some other term in the sequence. gives us another term. Now we need to be able to read the subscripts, so n is our starting point. So n minus 1 is the term directly before it. N minus 2 is the term 2 terms before it. So it's kind of saying to find the next term, you've got to know the previous and the one before it. Now what's the pattern that's set up? The term you're looking for is 3 times the directly previous one plus 4 times the one that was 2 previous. And they nicely gave us the first term and the second term. So when we're asked to write the first 5 terms, we should immediately write out, okay, the first term is just 1, the second term is just 2, that's given information. So the first one we need to find is the third term. So following the formula, if n is 3, this is equal to 3 times a sub 3 minus 1 plus 4 times a sub 3 minus 2. Now, of course, we can simplify that. 3 times the first term plus 3 times the second term plus 4 times the first term. What is the second term? It's 2. What is the first term? It's 1. 6 plus 4, and that would give us 10 is the third term. Now this would be a great time to pause the video and find the fourth and the fifth terms. Unpause to check your work. And we follow the pattern. The next term is always 3 times the previous term plus 4 times the one 2 previous, so that would be in this case 3 times the third term is 10 plus 4 times 2, and that would give us 38 for the fourth term. Following the same pattern, now it's 3 times the fourth term plus 4 times the third term would give us the fifth term. 3 times 38 plus 4 times 10, and we'd end up with 154 as the fifth term in this sequence. Now, often in sequences we have something called a factorial. It's going to be really easy to spot because it's always a number followed by an exclamation mark. And remember, if you see, for instance, 3, and this is read factorial, that is not equal to 3. So realize this is a particular symbol that represents a particular operation. What is the operation? If I'm writing 3 factorial, then that means I start with the number 3, and then I multiply down through the lower integers. So 3 times 2, always till you get your stopping point of 1. So 3 factorial really represents the number 6. 4 factorial, you always start at the number you're given, 4, and you multiply down through the lower integers, stopping at 1. 4 times 3 times 2 times 1. 4 factorial represents 24. Take a moment to find 5 factorial on your paper. That would be 5 times 4 times 3 times 2 times 1, which, if you calculate it, is 120. And here's a nice trick. Since it's going through the preceding values, do we see that 5 factorial is really 5 times 4 factorial? So if you know 4 factorial is 24, you could just quickly say it's 5 times 24, and you get 120 as well. Based on that reasoning, let's find 6 factorial. 6 factorial would be 6 times all the lower integers multiplied together, but that's the same as 6 just times 5 factorial. We know 5 factorial is 120, so that's 6 times 120, and we get 720. And definitely if you write out the multiplication in the long way, you'd still get the same thing. 6 times 5 times 4 times 3 times 2 times 1 is 720. So one thing that we notice is 6 factorial. 6 is a pretty small number, but 6 factorial, since it's a product of all the lower integers, is already a very large number. So factorials grow very quickly. And if we want to express a factorial in general, we would call it n factorial, and that starts at the integer n, and it multiplies through all the lower integers, so the next lowest integer is n minus 1, then n minus 2, n minus 3, and the dot 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 says continue this till you get to 2 times 1. Okay? And then this here, I meant to write this a little off to the side, it's a convention that 0 factorial is just known to be 1. So if you ever have to look at 0 factorial, just know that's set by a convention to have the value 1. Same thing, 1 factorial is just 1. So now that we understand this factorial notation, let's see how that could be used in a formula. Now first, think to yourself, is this an explicit or a recursive formula based on how it's written? It would be an explicit formula, right? Because there's no a sub something. It's just, if you know the value n, you're going to get the nth term by doing this. 5 times that value of n, all divided by n plus 2, find that sum first, and then apply the factorial idea. We're asked to calculate the first 5 terms, so let's work on that. A sub 1, 5 times 1, all over 1 plus 2 factorial. Now don't forget order of operations, parentheses comes first. So I think what is 1 plus 2? That's 3 factorial. 5 over 3 times 2 times 1, or if you already have memorized 3 factorial is 6, because that's always going to be a rule, you could automatically write this as 5/6. Let's find the second one together. A sub 2, so 5 times 2, all over 2 plus 2, then factorial, which you can mentally have written down as just 4 factorial. 5 times 2 is 10, over 4 factorial, and we can either write out what 4 factorial is, 4 times 3 times 2 times 1, and calculate that, or you can memorize 4 factorial is 24, and either way we get 10 over 24, which if we want to, we could reduce to 5/12. Now take a moment to find a sub 3, a sub 4, and a sub 5. I recommend you pause the video, attempt this on your own, and when then you unpause, we'll work through it. Now following along, we would have 5 times 3, all over 3 plus 2 factorial. 3 plus 2 is 5, so I could quickly write that as 5 factorial. And I get 15 over 5 times 4 times 3 times 2 times 1, and we might know 5 factorial is 120. Now, as you work through these, you might start to see a pattern, so you can always just write out the formula like I did in the first two step by step and simplify, or you could start to say, hey, look, these are multiples of 5 on top. So I had 5, 10, 15. By that pattern, I know I should expect 20 next on top, and the next one should be 25. What's happening to the bottom? It's just n plus 2 factorial, so at first it was 3 factorial, 4 factorial, 5 factorial. So if by that pattern, shouldn't I expect 6 factorial next, and then 7 factorial? So the nice thing about these sequences is they do follow these clear patterns. So once you kind of get a hang of the patterns, you can write down the later ones more quickly, or you can always go step by step. That works just as well too. Now we have to simplify this. This is 20 over 6 times 5 times 4 times 3 times 2 times 1, or 20 over 720. 25 over 7 factorial, or 7 times 5 times 4. Sorry, I missed the 6. You got to multiply by all the preceding integers. And 7 factorial is the same as 5040. And that's our first 5 terms. So here we've just got a brief introduction into how do sequences work, what do their formulas look like. We've talked about explicit formulas and recursive formulas, and we've also introduced the idea of factorials.